So last time we left off on chapter 3, we left off on butane conformations. Now we're going to go from two potential energy diagrams of the butane. So as I had discussed before, we have the total eclipse conformation in which we have methyl-methyl interactions. This leads to a higher energy of 5 kcal per mole. When we go down 60 degrees, we drop in energy because now it's gauche. The methyl-methyl are not on top of each other, but it's not fully to zero because they're next to each other. Then when we rotate it again, another 120 degrees, we see now methyl-hydrogen interactions eclipsed. This leads to higher energies of 3.6 kcal. And then finally, when we rotate it down to 180 degrees, that's the lowest point where there's zero, because it's an anti. We then rotate it again to 40, going back to the hydrogen-methyl interactions shown here. And then when we go another 300 degrees, we see the gauche methyl-methyl interactions. And then finally, we get back to the starting point, which is 360, is the totally eclipsed conformation. So you should be able to draw these types of conformational potential energy diagrams along with all of these Newman projections, energy landscape shown here. Steric strain exists in butane. If we see these methyl groups in butane when it's in the total eclipse conformation, they're so close together so that there exists some type of repulsion. This type of repulsion or interference between these bulky groups are known as steric strain, as you can see in this ball stick diagram as well as in this, or steric hindrance. Now, cycloalkanes are essentially circular forms of alkanes with the formula CnH2n. The smallest cycloalkane is cyclopropene, shown here. And then you can increase in size, and depending on how many carbons, for example, if it's 4, it's cyclobutane, 5, cyclopentane, 6, cyclohexane, 7, cycloheptane, and it goes on and on. So here are some examples showing the line structures in addition to the structures in which all the hydrogens are shown and the molecular formulas. In terms of physical properties of alkanes, they're nonpolar, relatively inert, and their boiling point and melting point depend on the molecular weights. In general, as you go from low to high molecular weight, you're increasing the boiling point as well as the melting point in general. So there are some exceptions. And if we look at nomenclature of cycloalkanes, cycloalkane is the main chain, and the alkyl groups attached to the cycloalkane will be named as an alkyl group. So if one alkyl group is only present, then there's no numbering necessary. And if we look at this example, we have ethyl cyclopentane, in which we have the cyclopentane group as the parent and the ethyl group shown here. If there are 2 or more substituents, number the main chain to give all the substituents the lowest possible number. So if we look at here there's 2 methyl groups, it's at 1 and 3, so this is 1,3-dimethyl cyclohexane. Shown here, there are 3 substituents, and you want to number it so that you have the lowest possible number. So there's 2 substituents off this carbon, so this would be your number 1 carbon, and this is number 3, but when you're naming it, it's named alphabetically, so it's 3-ethyl 1,1-dimethyl cyclohexane. Important thing to note is that oftentimes in exams, students accidentally draw structures when acyclic structures are intended. So try not to confuse drawing cyclic versus acyclic, vice versa. And always, if it's cyclic, they have the prefix cyclo. So you can also have cycloalkanes as substituents. The cycloalkane becomes a substituent when the acyclic portion contains fewer carbons than the cyclic part, or when there is a more important functional group in the molecule. So in all these cases, actually below, the parent is the cycloalkane. But if we look, an important thing to note is this is tert-butyl cycloheptane. Here is cyclohexane, but it's 1,2-dimethylpropyl. So again, numbering starts from left, from where the substituent is being joined to the main chain. So it's 1, 2, 3, and then you would add 1,2-dimethylpropyl. Geometric isomers, there's nomenclatures called cis and trans. Cis means on the same side, trans means on the opposite side. So as an example shown here, this is 1,2-dimethylcyclohexane, and so it is, and here it's 1-ethyl-2-methylcyclohexane. In this case, it's on the same side. As a result, you add cis. Note that cis is in italics. Again, for those of you in exams, if you're writing things out in italics, I'd like you to underline it and note that it's in italics, because it's hard for us to determine when we're grading whether it's just you writing it down in italics or not. Here, they're on the opposite sides. As a result, trans is now the prefix that you're going to be using. Again, this is italicized in the naming. In terms of stabilities of cycloalkanes, 5- and 6-membered rings are the most common in nature. Carbons of cycloalkanes are sp3 hybridized and require an angle of 109.5 degrees. When cycloalkane carbon has an angle other than 109.5, there will not be optimum overlap, and the compound will have angle strain, and we'll show examples of that. Angle strain is sometimes called Bayer strain in honor of Adolf von Bayer, who first explained this phenomenon. Torsional strain arises when all the bonds are eclipsed. And again, we'll show you of that. So here's angle strain in cyclopropane. Here's cyclopropane. The ideal tetrahedral angle is 109.5. However, in the cyclopropane, it's 60 degrees, so there's a 49.5 angle compression. The bond angles are compressed and they're bent, so you see bent bonds shown here of sp3 hybridized carbon atoms, and so this is what you have in cyclopropane. If we look at torsional strain in cyclopropane and we do a Newman projection, for example, we see that they're all eclipsed. The C-C bonds are eclipsed. As a result, you see these torsional strain that contributes to the total ring strain of cyclopropane. Cyclobutane, again, the ideal is 109.5 in a tetrahedral angle. In the case of cyclobutane, it's 90 degrees, so there's a 19.5 angle compression. When we look at a Newman projection of cyclobutane, they are eclipsed, in fact. So the angle strain, there's angle strain due to 90 degrees, and there's torsional strain due to the eclipsing bond in cyclobutane. When we look at the actual conformation of cyclobutane, we see that there's a slight fold where it's not necessarily 90 degrees, rather it's about 88 degrees in terms of angles. And so this non-planar conformation relieves this ring strain, and so this allows not quite eclipse, so that you can decrease the torsional strain due to this. This is called an envelope conformation. Cyclopentane, again, cyclopentane and cyclohexane are supposed to be the most common. There is an actual fold to cyclopentane, and if we look at it on our eye and draw a Newman projection, we see that there is a relief in the eclipsing bonds when it's folded. This envelope fold allows this kind of pucker, which allows relief of the torsional strain. Now, cyclohexane is the most common conformation, and the most common conformation of and stable conformation of cyclohexane is called a chair conformation, as shown here. This chair, it's called chair because it looks like a chair, And if you need to practice drawing them out, you should be able to draw these chairs where you have one end up and the other end down, and then you have these hydrogens either axial, which is going up and down, or equatorial, which is on the equator of the actual ring. And if we draw a Newman projection shows that they're not eclipsed and they're all stable. The chair is the most stable conformation, a null isomer of cyclohexane. The chair has no eclipsing interactions. Bond angles in the chair are actually 109.5, and so everything is nice and stable. In addition to the chair conformation, cyclohexanes can undergo what is called a boat conformation. In terms of a boat conformation, now you have both of the flaps up. This is a symmetrical boat where if you look at down your eyes, down these two carbons, you can draw the Newman projection, and in the Newman projection of a boat, all of the hydrogens are eclipsed. So this is a slightly higher in energy conformation, and because it is eclipsed, it'd rather undergo a twist boat conformation in which you see this twisting occurring to relieve that torsional strain. So eclipsing bonds result in torsional strain in terms of boat conformation. The twist boat conformation has fewer eclipsing bond interactions and less interference between flagpole hydrogens. So if we look at a conformational energy diagram, and you should be able to do this, here's your energy, here's the different conformations, starting off with one chair, and this where the fourth carbon and the one carbon of the cyclohexane is pointing up and down respectively. Now as we go to the boat conformation, you go from that one end going flat across, so you're pushing this up, leading to what is called a half chair, so that's the highest in energy. Then you get to this twisted boat conformation, which we talked about, and then to the boat conformation, in which now you've made that down pointing one carbon all the way up, and then now you're going to change this side and bring that down, and so that will undergo a twist boat conformation, which then you have a half chair going to the full chair, and now what you've essentially done what is called a ring flip, going from here to here. Axial and equatorial positions I've mentioned before and now highlighted here. Axial bonds are in the red shown here, are the ones that are directed vertically parallel to the axis of the ring. So all the reds up and all the reds down, those are axial. Equatorial are the ones that are directed outward toward the equator of the molecule, and so you can see them, and each of the equatorial bonds are actually directly slightly up or slightly down, right? So they point slightly up or slightly down, etc. So you should be able to draw all of these, and I would suggest you practice drawing them, so especially for exams, because you should be able to draw them very quickly, with denoting that some of them coming up, some of them are coming down, which ones are equatorial, which ones are axial. And this is just to show you, yes, the equator ones kind of follow the rim of the ring, and the axial ones are on top and on the bottom. You should also use your models to show this and show the actual ring flips that I had talked about in the previous slide. So chair-chair interconversion, we had just shown that in the energy diagram. So you're going from one chair conformation to another chair, in which now the 4 carbon moves up and the 1 carbon moves down, showing here and shown here. And then in that conformation and interconversion, it undergoes a boat conformation. Now, so if you notice, the axial methyl group of this methyl cyclohexane is up. When it undergoes the conversion from this to this, it goes equatorial. It's equatorial facing up. Now, of these two conformations, this one is high in energy and this one is more stable. So if we look at axial methyl interactions in methyl cyclohexane, here, if you look down these two carbons, carbon 1 and 5, you can see that this methyl is gouged with this CH2, and if we look at the Newman projection, we can see that. If we look at it from here, where you're looking at carbon 1 and carbon 3, again, if you can see that this methyl is gouged with this methylene, and the Newman projection here and here. So you should be able to make these molecules go from kind of line drawings to Newman projections, especially with cyclohexanes. So in terms of equatorial methyl groups, shown here is if you look at this molecule where the methyl group is now anti to this CH2 group on the 3 carbon, we'll see that yes, it's anti, and here it's in the equatorial position in terms of Newman projection. 1,3 diaxial interactions are when you have a methyl group that, or a substituent that is in the axial position and then exhibits repulsion with the 1 and 3 interactions. And so as a result, if you have the methyl group in this case axial, it'll exhibit 1,3 diaxial interactions, allowing for repulsion in which it's not favored. As a result, it would prefer to be in the equatorial position because it's more stable by 1.7 kcals per mole. In terms of tertiary butyl cyclohexane or tert butyl cyclohexane, look again, tert to tert group is in italics. You see in the terms of 1,3 diaxial interaction, this is extremely crowded, more so than a methyl group. As a result, it's strongly preferred that the tert butyl group is actually in the equatorial position. Cis 1,3 dimethyl cyclohexane, as an example, also exhibits 1,3 diaxial interactions. These are extremely unfavorable. As a result, they would really prefer that these two are equatorial and stable. So in this case, if you look at the arrow is strongly favoring to the diequatorial state for the dimethyl cyclohexane. In the case of trans, again trans being in italics, the 1,3 dimethyl cyclohexane shows that both these conformations, when you do a ring flip, are actually in the same energy state. Because in one case we have one axial and one equatorial. When we do a ring flip, that axial becomes equatorial and that equatorial becomes axial. As a result, they have the same energy. Cis 1,4 ditert butyl cyclohexane. Here in the 1,4 position, if they're on the cis, they're on the same side. You have one axial and one equatorial. This axial is again very disfavored. You have 1,3 diaxial interaction. Interestingly, the most stable conformation is this twist boat conformation, in which both of these tertiary butyl groups are on the equatorial or on the outside surface, so that nothing is actually in the axial position. So if we look at a problem in this case where we say draw both chair conformations of cis 1,2 dimethyl cyclohexane and determine which conformer is more stable. Repeat for the trans isomer and predict which isomer, cis or trans, is more stable. To answer the question, there are two possible chair conformations for the cis isomer, shown here, right? In which one is in the axial and one is in equatorial. If you do a ring flip, you see that one becomes axial and the one that was equatorial becomes axial, and the one that was axial becomes equatorial. They are the same in energy, and so that is the solution to A. In the case of the trans isomer, trans where you have two of them now in the axial, and this would be diaxial, then when you do a ring flip, you have them diequatorial, and this is going to be most favored, and this will be the stable conformation. So of the two, the trans is more stable because the trans isomer can be in the di-equatorial conformation, which is about 1.8 kcal per mole lower in energy than either conformation of the cis isomer. Remember that cis and trans are distinct isomers and cannot interconvert. Another problem, draw the most stable conformation of 1-ethyl trans, 1-ethyl 3-methylcyclohexane. So first you want to draw the two conformations shown here, right? So you can have one axial, one equatorial, and then you do the ring flip and now it becomes equatorial and this becomes axial. So the ethyl group is bulkier than the methyl group. As a result, you don't want this in the axial state. Rather, you'd prefer to have the methyl group in the axial state and this in the equatorial. As a result, this conformation is the most stable. Now, bicyclic systems are there are three types of systems that are bicyclic. One is a fused ring. Fused rings actually share two adjacent carbon atoms and the bond between them. So here's a fused bicyclic structure. Bridge rings share two non-adjacent carbon atoms and one or more carbon atoms, the bridge between them. So here's non-adjacent and the bridge So these would be the bridge head carbons. So this would be bicyclic, or not. They are bicyclic, but these would be the bridge systems. And then spirocyclic compounds, which are rare, are when two rings share only one carbon. So here would be a spirocyclic. Now, in terms of naming the bicyclic systems, you have the prefix bicyclo, and then in brackets number dot number dot number, and then whatever the alkane is. So the alkane is the total number of carbons within the cyclic system. So for naming this, for example, this is 1, 2, 3, 4, 5, 6, 7, 8. So that would be an octane. And then bicyclo is the prefix. Now in terms of the numbers are the numbers of carbon on the bridges in decreasing order. So if we were looking at the numbers, we're going to start with the highest number and go to the lowest. So there are 4, and then 2 and 0, so it would be 4, 2, 0. Bicyclo here would be, this is an octane because there's 8 carbons. In terms of numbering, it would be 3, 2, and 1. So decalin is the final structure shown here. You can have it as cis and trans decalin, right? Cis on the same side, trans on the opposite. You should use your models to actually build these structures. In the case of cis decalin, you're going to have, right, your chair conformation fused to another chair conformation. In one case, the H is equatorial, in the other case, the H is axial. In the case of trans decalin, you're going to have that same ring structure, which are fused, where one is axial and the other one is axial as well. Here's the bridgehead carbons in both cis and trans. Of these two, the trans is more stable because the alkyl groups, meaning these groups, these over here, are equatorial. In this case, you have one axial showing here with the actual methylene group. And so therefore this is more stable. And so this ends the chapter 3 for the class, and so you should again do many problems as possible.